welcome to CEC lectures. Myself Dr. Preeti Jagmani. I am an associate professor, Department of Computer Science, Aryabhat College, University of Delhi. So in the last couple of lectures we have begun with our new series, which is advanced data structures and algorithms, and in the last two lectures we have seen one data structure named as skip list, and we have also seen that what exactly is the kind of application scenario of a skip list, or what is the we can say requirement of the skip list, on in which kind of scenarios this skip list is going to be kind of used. On the similar lines, we are going to study a new data structure in today's lecture, which is named as tries. So let us first build the background that why these tries are important, what kind of application these tries are going to handle, and what is special in these tries which is not available in already existing data structures, in the sense that all the data structures which we are already familiar with. So what is the problem with those data structure which is kind of being taken care by this tries. So tries basically is required in some typical kind of scenario. So for example, my application scenario is it's a kind of seamlessly simple scenario which is kind of representing a set of words. Now representing a set of words inside computer memory is actually such a scenario which is not very complicated, I am sure, and there are many solutions which are available for this particular thing. So for example, we can have a hash or maybe a dictionary are these the solutions that we are probably familiar with, as with the hash table. Now, to solve this very problem of representing a set of words, we are going to use a trie. So trie is spelled as TRIE, and if we want the plural thing, we will say TRIE. So this term trie actually comes from the word retrieval. So in retrieval, if we remove the RE from the beginning and VAL from your the last thing, it will become a trie, and it is pronounced as try. Why it is pronounced as try or try? Just to kind of differentiate it from other tree structures. It is not pronounced as tree, it is pronounced as try or tries. So the pronunciation is different, just to have a kind of have a difference, a line of difference between the two. Now when I am saying that I am looking for a simple problem which is nothing but the representation of set of words. Now in this context, if you are aware with one of the pattern matching problems, and these pattern matching or these string matching problems can be solved through various ways. One of them is the the most basic, the naive string matching algorithm. Another one is the Kunt-Morris-Pratt, which is KMP algorithm. Now what do we do in this KMP algorithm? We pre-process the pattern. The pattern means the smaller text which we are looking for in a larger text. So for example, in a document or in a file, I am looking for a particular word, let us say college. So that college is a pattern. So pre-processing of pattern takes place in this string matching algorithm, for example Kunt-Morris-Pratt KMP algorithm, and because of this pattern pre-processing, the speed of the algorithm gets better, and that KMP algorithm performs the pattern matching in time proportional to the text size. So that is actually a kind of improvement, we can say. But what will happen if the text is large, text is immutable, and text is something which is looked for often? So for example, let us say something like looking for Premchand or looking for Shakespeare on Google. So, in this situation your text is quite large because the kind of material or the information about the Shakespeare or information about let us say I am talking about Narendra Modi is going to be huge, and we may want to process the text instead of patterns. So, here we will not be processing the text, we will not be processing the pattern, that means the keyword which we are looking for, but we will be processing the text because I am assuming the text is large, as it is large, and it is also kind of immutable and searched for often. So, here what I am trying to establish is the problem of pattern matching. In this problem of pattern matching, the a very kind of useful data structure, a trie can be a very useful data structure because it is actually regarded as a compact data structure which is used for representing a set of strings, and these set of strings we can take an example such as all the words in a text. Which all the words in a text I am talking about, that I will let you know in a short while with the help of an example. And the and a tries support the pattern matching queries in time proportional to the pattern size. Now, this is very remarkable, this is very important, because if I am talking about the text, the text is large and the pattern which we are looking for into that text, for example college, is smaller. So, your trie is going to support the pattern matching query in such a way because of its structure, because of its characteristics, because of its properties. So, the trie supports the pattern matching queries in time proportional to the pattern size, and hence we can say that this trie is actually a data structure which is kind of we can say much affordable or much suitable for the pattern matching thing. Now, before looking into the structure of this trie, what kind of data structure it is, let me mention here this trie for the trie memory for computer searching was first recommended by a French scientist, which is Rene de La in 1959. Now, what does this trie do? This actually trie is going to save memory space at the expense of running time. So, for example, if we use a linked list for each node vector, since most of the entries in the vectors tends to be empty. Now, this is a common scenario that if we are looking for or if we are using a linked list for each node vector, most of the entries in the vectors tends to be empty. So, basically what your trie is doing, your trie is actually kind of establishing a compromise between the running time and memory. It is saving memory space at the expense of the running time. Now, how this trie is going to be kind of arranged, that we are going to see shortly. So, and how this trie looks like. So, this trie basically, as I told you, that this is pronounced as trie just to differentiate from the tree data structure. Now, why that is important? Because trie itself is basically a tree data structure. It's a kind of non-linear data structure in the form of a tree. Now, while getting this tree created, or while this using this tree or updating this tree, some rules are to be followed in terms of how it is to be created, how it is to be updated, and so on. And those rules we will be also looking at. Now, every now you are aware of that if I am talking about the tree data structure, it will be a data structure which is formed with the help of nodes and I can say links. So, it kind of where here the nodes stores the letters of an alphabet, and by structuring the nodes in a particular way, I can say structuring the nodes in a sorted way, the words and the strings can be retrieved from this trie data structure by traversing down a branch path of the tree. I am just repeating it again, that by structuring the nodes in a particular way, words and strings, we can retrieve words and strings from this tri-data structure just by traversing down a branch path of the tree. So, we will be following a particular branch, we will traverse down, and with the help of that traversal, we will be able to kind of retrieve words and strings. Now, if I am talking about a tri, a tri has an empty root node. The root node within a tri is always empty, and with this root node, it is having links or references to the other nodes. Now, how many links or references I am talking about? It is it could be one for each possible alphabetic value. So, for example, this root, I am having an empty root node, and from that, if I am dealing in the strings of English alphabet, so there are 26 alphabets. So, a link or a reference I can say to the node A, then a link or reference to the node B, and then a link or reference to the node C, and so on and so forth. So, each tri will be having an empty root node, and it will be having links or references to other nodes, one for each possible alphabetical value. Now, the shape and structure of a tri is always a set of linked nodes connecting back to an empty root node, we can say, or we can just follow the first statement which says the shape and the structure of a tri is always a set of linked nodes. Now, how many number of child nodes will be there in a tri? That depends on the total number of possible values. So, for example, as I have told you that I am assuming that I am representing the English alphabet, then the total number of child nodes is directly connected to the total number of the letters possible. So, total number of letters possible in English alphabet is 26. So, the maximum number of children a particular node can have is nothing but 26. So, in order to guess the structure of the tri, let us look at the figure which is given on the screen. Now, this is a standard tri. Why I am saying this is a standard tri? Because in upcoming lectures we will be also looking into a compressed tri and so on and so forth. So, this is basically a standard tri, and this standard tri is made for the set of strings. The set of string is denoted with the letter S, and what all strings this tri is being denoting, these strings are bear, bell, bid, bull, buy, sell, stock and stop. Now, what is particular about this string set S? The letters or the strings which are being which are the elements of this set are actually starting from the two letters only. One is B and another one is S. So, bear, bell, bid, bull, buy, sell, stock and stop. So, this is kind of a I can say it is a set of strings with 8 elements, and all these 8 elements are either beginning with B or beginning with S. Now, what is happening here? So, we have an empty root node, and because in the set we have only 2 starting letters. So, the 2 references will be there, or the 2 links will be there, one which is going towards B, another one which is going towards S, because that is the kind of I can say common letter, or the first letter is common. Then from B, if you can see on screen, we have a figure here. So, from B, let us trace down the leftmost path. So, from B, the leftmost path says E and B, then E, then A and R. So, in this way, a string which is bear is being represented with the help of a tri, which is given here. So, B, E, A, R. So, the empty node and the first branch which is going towards the leftmost direction is BEAR, and R is being kind of enclosed in a square node, which you all are aware that it essentially means that this is the kind of leaf node. Now, for example, one thing which is also you must notice here, that in this set which is bear, bell, bid, bull, which I have shown you, all the strings are arranged in alphabetical order, and hence we are going to kind of represent them using this alphabetical order only, and that is why I have told you that the arrangement of nodes is going to be very kind of particular when I am talking about a trie. So, BEAR is there. Now, if I am talking about the next string which is bell, so you can see that, so we have B, then we have E, and on the right side of E there is a branch which is going on and having two L, one L and the another one L, which is the leaf node. So, if you can see the leftmost subtree of your trie which is shown on the screen, so we have BEAR and then we have BELL. So, BE, that is the I can say common portion which is belonging to both the strings bear and bell, and if we want to represent bid, so the only first letter is common, so we will start from B and then we will come down to I and then there is a D. If we want to represent bull and buy, we have common as B and U. So, B is the first node after the root node, then we are coming down to U and then LL on the left side and BUY by on the right side. So, basically this particular trie is having I can say two subtrees. One subtree is representing all the strings which are beginning with B, right subtree is representing the three strings which are starting with S, and whatever is the common between the strings that is not being repeated, the string is kind of I can say represented on a path downward, and then it will split into the branches when there is an a portion which is uncommon between the two. So, for example, if we talk about bear and bell, so B and E is the common portion, so can be taken with the help of only one we can say one branch, while after B and E this AR and LL is the portion which is kind of I can say separate. So, BE, the one branch will lead to AR, another one branch will lead to LL, and similarly for bid we do not have anything in common except B, and then for bull and buy we have common as B and U, then LL and Y on the next branch. Looking at the right subtree, we have this right subtree which is starting from S. Now, if you can see in the string set S, we have three strings starting from S. One is cell, another one is stock, and third one is stop. So, cell is going to be the leftmost because of its kind of arrangement. So, E comes before T. So, cell, so starting from S and then ELL. While in stock and stop, if we can see the three letters which are common are S, T and O. So, S, T and O are coming through a common branch, and then this branch is being splitted into the two. One is going as STOCK for the term stock, and another one is going as STOP which is for the word stop. So, by this arrangement, I am sure that you must have got that what kind of data structure I am talking about. So, if I am representing an English alphabet, so each and every node can have 26 children, at most it can have 26 children, because there are only 26 letters in the alphabet. And let us say for example, I am representing some binary string. So, binary alphabets, just we have just two, 0 and 1. So, each and every node can result into the two sub nodes, one is starting from 0, another one is starting from 1. So, one node can have 26 children if I am talking about alphabet, English alphabet, and if I am talking about the binary alphabet, your one node can have at most 2 children. So, what I am trying to establish here is a trie could be pretty small or pretty big depending upon what it contains. So, that essentially means that what it is going to contain, either it could be a pretty smaller trie in terms of width I am talking about, or it could be a very big trie also. So, a trie is basically a data structure with an empty root node as you have just seen, and it is having the references to children node. And if we observe this children node in a trie, that single child node in a trie is containing what? It is containing actually two things. One is a value which might be null, but in the example which I have just shown you, that those children with null value are not being shown here. Otherwise, the branch corresponding to A, then the branch corresponding to C, and then the branch corresponding to D, all must have been kind of shown. So, we have not shown it that way, but a single child in a trie can contain just two things. One is a value which might be null, another one an array of references to the child nodes, all of which also might be null. So, this is basically, I can say, this is how we are going to describe the structure of trie, and each node in a trie, including the root node itself, will have two aspects to it. And I have already told you that the trie which is representing the English language, when it is being created, it consists of a single root node. That empty single root node in case of English language is usually set to an empty string. And then this root node will also have an array that contain 26 references, all of which will point to null at first, and as the trie grows, those pointers start to get filled with the references to other nodes. So, initially when you have when you are starting your trie creation, the root node is going to be empty and all the references are empty, and as you keep on adding strings into that as you keep on adding strings into that set S or into the representation of trie, as the trie grows, those pointers started to get filled up with the references to other nodes. And as you have seen that trie is, yes, it is a tree based data structure, but it is a, I can say, sorted tree based data structure that stores the set of strings, number of pointers equal to the number of characters of the alphabet in each node, that we have already established. Now, it can search a word in the dictionary with the help of the words prefix. So, whatever prefix, because we start from, let us say, beer and bell we are talking about. So, the common portion in the starting is B and E. So, it can search a word in the dictionary with the help of words prefix. So, when I am searching for a word in a dictionary, that is the common pattern. We start with B, then we jump to E, and then we go to A, R, and so on and so forth. Also, one thing to mention here is that tree is this trie is also known as digital tree or prefix tree, and the position of a node in the trie determine the key with which the node is connected. So, the position in the last, so that means the key is in that sorted order, that key is coming in the last, we can say. Now, looking at the while building this foundation about tries, let us look at the properties of the trie. which is particular for a set of strings when I am talking about the English alphabet. So, the root node of the trie will always represents the null node, and I have already told you that this is in case of an English alphabet will be represented by your empty string. Each child of nodes is sorted alphabetically, that we have already established. Each node can have a maximum of 26 children, which is equals to the size of the alphabet, and each node except the root can store one letter of the alphabet, because the root is going to be empty and it will store the empty string. So, in this lecture what we have covered is basically we started with a trie and we looked into that kind of pattern matching, a bit of pattern matching, matching fundamentals, why trie is kind of mostly used in these type of scenarios. The detail is yet to be built. Then we understood the structure of the trie with the help of an example, and then finally we looked into some properties of the trie for a set of the strings. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this. Thank you for a patient hearing. I will see you in the next lecture. Till then, take care. Goodbye.